Okay, so thank you all for coming. So I will start. So please interrupt me if there is some brief remark. Then there will be a lot of discussion after. Okay, so I talk about geometric interpretation of the standard model, mainly with topological excitation. So basically we know that apple plus apple equals 2 apples, but it's true, but it doesn't say much about what is apple. So here we have the Feynman diagrams. We split the scenario in perturbative QFT into Feynman diagrams. But the question is, what is in single diagram? What is the field configuration represented by such a single diagram? So we'll focus on such classical configurations and to finally use the smoothing into Feynman ensemble. Yeah, so having such single diagram, if you have electron here, then there is associated electric field, magnetic dipole moment, but also angular momentum. There is some rotation, not of the electron itself, but of its field alone. So then for electron, for example, we should be able to understand the field down to zero, down to the center of electron. But there is the problem of infinite energy. We regularize it. So as usually it is done after the second quantization, here we do it before. And this regularization will lead to running coupling corrections of the Coulomb interaction. So for very short distances, that means very high energy. So the central idea here is looking at the Gauss law. So the naive Gauss law gives a charge being a real number, while in nature it is integer multiplicity of elementary charge plus quarks I will talk about. So the question is how to enforce in this field the charge quantization in the Gauss law, and it can be done by Manfred-Faber's way by interpreting field curvature as electric field of some deeper field, like in this diagram below. This way, the Gauss law, as in this topological version, we count topological charge. Yes, so interpret this curvature as electric field. This way, the Gauss law gives topological charge, which has to be quantized. Yeah, so finally, I used this kind of Lagrangian, which is F mini, like for electromagnetism, but using F as dual curvature. So it's crucial that we use dual curvature, replace electric and magnetic field. Because otherwise we would have magnetic monopoles. While in nature we don't have magnetic monopoles right there. We have only electric monopoles. So thanks to using dual formulation, we have only electric monopoles, charges. And finally, I need full curvature with 4 indexes, because finally curvature has 4 indexes, and doing so, I will get unification also with other interactions. So I assume that there is some deeper field M, which will represent this shape of the molecule, like here. So it's called Landau-de Gennes model in liquid crystals. It's very similar. So here we have these few basic topological defects. So one is the Sine-Gordon model, one-dimensional, quantized charge, special relativity. Then going to 2 dimensions. So here is a liquid crystal, basic topological defect. Then we have interaction, putting topological defects in various distances. We get effective Coulomb interaction. So here is in 3D such model of electric charge as topological defect. Soliton. And then finally, we also have for electron, also magnetic dipole moment. So it's more complicated. So here I will try to convince you that this is nice viewed for electron. Also with magnetic dipole moment, angular momentum, and clock. Okay, so let me continue. Okay, so the Sine-Gordon model, so we probably know well. So this is very nice picture from Manfred Faber's article that it can be realized, but literally a lattice of pendula connected with a spring. So the spring makes them, they prefer similar angles. The gravity prefers them going down, but down, there is one down, and there is 2 pi farther, there is also down. So we can get this transition from one vacuum, this minimum potential to another, and minimize this configuration. And it has to have some energy. So this is kind of mass of this particle. So it becomes literally a massive particle. So it will be restricted to finite velocity. It cannot reach the speed of sound here of propagation. And reaching this speed of sound of propagation, there is Lorentz contraction, like in this photo. It is traveling king, so it is resting, it is traveling. You can see it's literally contracted. So it already creates many particle physics phenomena. So we have also quantization. We have king, anti-kings. Yeah, so it's a very nice model to start with. And then we go to two dimensions. Okay, so there are these well-known topological defects in superconductor, super fluid. Yes, so in superconductor there is quantization of magnetic moment because of change of phase. Order parameter has to be 2 pi times an integer number. In superfluid of angular momentum. And in QCD, quantum chromodynamics, there are also used very similar pictures. They assume, for example, in quark-gluon plasma, they assume it's approximately superfluid usually. Then there is this quark-antiquark pairs with usually we assume some because of vortex topological between them. So I will have to extend this topological vortex by charge. So quark are believed to have fractional charge, 1/3, 2/3. So how to do it? So we have this vortex here. So here is minimum energy, and then we have rotation inward outward of the field. Having full rotation by pi of this field inward outward, then you would have topological charge. So we've got elementary charge. But performing only fractional rotation, we can get like quark-like structure. I will show further why baryons enforce these fractional charges. And between there's a conflict. There appears conflict, so there is increased energy. So exactly as expected for these color strings in quantum chromodynamics between quarks. So this is very high energy, making the quarks confined very close together. Okay, so a very natural way to model these kind of objects are liquid crystals. Yes, so there are many articles that when they get long-range interactions between such topological defects, like here. So, for example, they put such two topological defects and look at their positions, and with time it agrees with, for example, Coulomb, 1/distance, dipole, quadrupole interactions. So they can get long-range interactions with them. Also, there is this analogy between electrodynamics and hydrodynamics, especially superfluid. So here we assume this is liquid crystal, but superfluid liquid crystal, the model I'll talk about. So there is mathematically they are very similar. We use this similarity to try to recreate electromagnetism also as some superfluid dynamics below. So then for such topological defects, there are many articles testing the quantum behaviors. For example, interference, for example, because of bomb effect, tunneling. Also, there are these very nice bouncing droplets, classical objects with wave-particle duality. That there is this shaken surface, and there is a droplet which has coupled wave around. And for example, they recreate the double-slit experiment. So for single droplet, looking at statistics, they get this interference pattern because the droplet travels one trajectory, but its coupled wave, pilot wave, travels all the trajectories. And most interesting, they also get the orbit quantization. So they get these orbital trajectories, but not any. There are integer of them. So because the coupled wave has to become standing wave, like in stationary Schrödinger equation. So having they already recreate a lot of quantum mechanics this way. Okay, so here is the main picture again. So I go through. So the main motivation is to repair electromagnetism. It has two problems. So one problem is is infinite energy of the point charge. We need this regularization. And the second is that the Gauss law gives a real number, while in nature it gives integer number. Yeah, so lack of charge quantization. So for the second, we interpret this topological Gauss this called Gauss-Bonnet theorem as the Gauss law. So by interpreting the curvature here as electric field, and for regularization, they will use Higgs potential. So like here we have unitary vectors, but there is Higgs potential. So if you having to use unitary vectors down to the center of the singularity, it would have infinite energy. But to avoid that, the field is regularized to zero vector here. Yes. So we can regularize the singularities to finite energy. And it will correspond to the running coupling corrections to Coulomb interaction. Okay, so here we go to this basic topological charge, like Hedgecock, and now, but we have many more particles. For example, 3 leptons. So we go to this in liquid crystal. They call this Landau-de Gennes model. that we start recognizing twist of these n vectors here. Yeah, so we have now field of 3 different axes. And so, for example, to perform this hedgehog as topological charge, we can do it with first axis, second axis, or third axis. So we get three realizations of this unitary charge because we live in three dimensions, and so they have the same topological charge but different mass, different regularization. So kind of resembling the 3 leptons. Additionally, trying to align the second axis on the sphere, we cannot do it because of the Higgs-like theorem. So there is additional conflict there, so which can be seen as that they are no naked charges. That charge has to also have magnetic dipole moment. Yes, so it's not perfectly spherical. It has to have this magnetic dipole moment. There are tiny magnets also. And finally, going to 4 dimensions as space-time, we added another axis. So now it's our time direction. So it should be the longest. They have the highest tendency to be aligned toward time direction. So they are kind of local time directions. And then we give second set of Maxwell equations. So for unification with gravity. So we automatically get also unification with gravity. This twist here recognized for the n field corresponds to quantum phase with much low energy dynamics. Okay, so from philosophical perspective, so let's think about this classical quantum picture. So, for example, if you're having these couple oscillators, we can think about them classically, but we can go to normal modes, and we have kind of unitary evolution. So it's already kind of quantum description. Then going to lattice of pendula, so we get classical description, but we can also go to normal modes, being phonons and behaving as quasi-particles, for example, in quantitative, in quantum field theorem. Then going to continuous limit, it's becoming much more complicated. So we have this. I've mentioned there is, for example, this orbit quantization observed for these classical wave-particle duality objects. But the most interesting for us here are the situation of varying number of particles. Yeah, so what is the central property of quantum field theory as seen? So it is also a property of this soliton, topological soliton models. So for example, here we have no particles. Here we have a charge electron charge antiparticle pair from nothing. We could also have some vibration interaction as kind of virtual particles. So from one side, having these topological defects and trying to consider scattering on them, we should use ensemble of the parameters we don't know. So we should use some Feynman diagram ensemble because we don't know all the parameters of the field and so on. Integrate often the momenta. So finally, to practically work with them, we also would need to go to perturbative QFT. From the other side, having such diagram, Feynman diagram, the question is what is the field it describes, this abstract diagram? Yeah, so what is hidden behind this electron and so on? So what is the field configuration? So this is not about some different view. This is just different perspective on the same system. Yeah, so we should think about it like this. Okay, so now going to this mentioned electron. So it is usually imagined as a perfect point, a result of electron creation operator, but it is extremely complicated configuration of fields. So for example, this electric charge and magnetic dipole and gyroscope, angular momentum, which has to be somewhere there in the fields. So the fields, not the electron rotates, but it's field alone. And finally, there is also the clock, the Broglie clock, Zitterbewegung. So it is required by the same formula as neutrino oscillations that we should be able to put this energy here as the mass in Schrödinger equation. Yes, so if you put mc square energy of electron into Schrödinger equation, so in any relativistic quantum mechanics, usually it is used in Dirac, then it requires some oscillation. So for electron, it's extremely fast. Like 10 to 20 hertz. So it is confirmed in various solid state models, and there is also direct confirmation in this article, Guarane famous experiment. So how did they confirm it? So they used very high energy electrons, ATMF electrons. This way, thanks to time dilation, the distance between ticks of this clock start to agree with lattice of crystal, silicon crystal they use. So getting this resonance between this temporal clock of electron with spatial lattice, they get increased absorption. So this is the absorption depending on the parameter. So indeed there is some resonance between the clock and the crystal. So, but also this is the same formula as used for neutrinos. So I don't think there should be doubts about this. So the question is how to combine all these four properties into one field configuration. So it has to be quantized charge. So here is hedgehog, but also for magnetic dipole, it has to be some asymmetry. Then we need some literally rotations of the field, also required for magnetic dipole moment here. And this rotation also works as clock. Yeah. So finally, suggesting this kind of model of electron that there is this field, and this field twists all the times with this speed 10 to 21st hertz. The big question is what propulses this clock. This difficult question. I have some mechanisms, but it's a difficult problem to answer in the future. Okay, so maybe let's take a brief look at the mathematics of the model I'm working on. So we work on vacuum, which is SO13 Lorentz group. So very basic group. So I look at dynamics. So here is this dynamics as its connection. So going this direction, how the field locally rotates. So having these elongated molecules, there is this tilt like this high energy tilt and low energy twist of this molecule. So here is gamma 1 is this twist, low energy twist, and the gamma 2 and gamma 3 are the high energy tilts. Yes, but we have also the 3 boosts. Yes, so here is this M field is this rotated and boosted this molecule of shape given by the parameters. So it has 4 parameters. This one corresponds to electromagnetism. This delta corresponds to energy contribution of these twists. For example, looking at Lagrangian of QED, we can see that we have F mini electromagnetism, but we have tiny contribution H bar times C of these twists. Yes, so there is also, it unifies both the twists and electromagnetism, and we also need to do it. Yes. So here we do it by these tilts of this molecule and twists of this molecule to unify both these low energy twists and high energy tilts. And finally adding these boosts, we get a second set of Maxwell equations. So it's called gravity electromagnetism. Yes, so literally like electromagnetism, but with different constants, and we've changed sign here. Yes, this is very important. So as here, yes. So we get automatically this unification with GAN, also interaction between electromagnetism and GAN. So it is crucial, for example, to get light bending because it slows down electromagnetic propagation in high gravitational field. So the Fermat principle gives us the light bending. Also time dilation. So if we slow down electromagnetic propagation, then everything slows down. But we have also the direction deforming the shapes of these molecules. So here are at the bottom. So here is, so we change this diagonal here, yeah. So we modify this diagonal. So there are these additional terms which I think agree well with gluons and Higgs particle contributions, but I will have to work further on that. But basically, I think it should be there. So a basic argument is that it will be also governed by wave-like by electromagnetic like Lagrangian, but it's short range because it only works when the potential is activated, where we deform this molecule, and it only happens very short to particles. Yeah, so this is electromagnetic like interaction like in the Young-Mills gluons, but working only very close to particles. Yes. So it agrees with QCD. Okay, so here is another view on this Lagrangian. So here is this full Lagrangian F mini with full curvature plus Higgs potential, which prefers this shape of molecule kind of, yes. And this is the F, which is both curvature but also containing the weights to get different types of long-range interactions, electromagnetism, gravity, and Klein-Gordon like for quantum phase. And also gluons if going out and Higgs if going out of the potential minimum, the vacuum. So here is a view for electromagnetism. So we believe that electromagnetic field has some deeper a field. Yeah. So it's not the deepest. So here we say that there is even deeper field. I call it M here because we need charge quantization. Yes. So A cannot be any. It has to be such that when we calculate the Gauss law, it gives integer value. So to make it, we need to get some even deeper field, this M field, which is kind of generalized field. So generalized phase. So we have quantum phase, but we also say that there is a phase in space around. So for example, this momentum operator, here, this derivative, and A also has a derivative of the deeper field. Yes. So this A in fact is also a derivative here. So here is this F mini calculated with Mathematica. So we get these various curvatures, and here we can see that this electromagnetic curvature, this crucial. Here is this much smaller, this H-bar type correction, the contribution for quantum phase, for Klein-Gordon-like equation, and here is the gravity contribution. But also going from this Lagrangian to Hamiltonian, turns out there are also negative energy contributions. So due to signature of the space-time, so here you have see that there are some negative contributions, like this gamma 1, gamma tilde 3. So in gravitational field, this tilde contribution, there is preferred this twist. So this is literally an energy preference of periodic process in gravitational field. So this is exactly what is needed for the clock. So I hope to get the clock, but it's quite really complicated calculation. So if somebody could help me, it would be great. Okay, so there are related models, so-called Skyrmion model. There is a large group around them. So they imagine nuclei usually and neutron stars with this kind of topological solitons, interpreting baryon number as topological charge. So instead of electric charge, they interpret baryon number as electric charge. So this is one difference. But the more important difference is that they have vacuum with single minimum. So far from the particle, the field goes to this vacuum. So they have only short interactions. So they don't have electromagnetism. Proton and neutron are practically the same then. So we instead use this non-trivial vacuum. So we have this Higgs-like potential and dynamics inside this Higgs-like potential minimum, this vacuum gives electromagnetism in Manfred's way, and in mine also quantum mechanics and gravity. So as kind of Gauss boson, these zero modes of this in this potential. Okay, so let's look at the topological charges in 2D and 3D. So in 2D, so here is some vector field, and to define a topological charge, we make a loop around this defect and calculate how many times the field rotates. So here it rotates once. It also rotates once. But we can see that this is Gaussian invariance. We can add some global phase, and this is the same topological charge. Yes, here it performs -1 charge, so here's -1. Here it performs +2. But here, if you look at it, if you go around, the field goes upside down. Yes, so it performs half rotation. So it is +1/2 charge, topological charge. Here is -1/2. So we can get fractional charges because here field up and field down is the same field because we have a symmetry of the field. What is common in liquid crystals? So they get this kind of topological vortices, they call them destinations. So we can get one-half. And looking at definition of quantum rotation operator, it says that rotating spin S particle by theta angle, the phase should rotate by S times theta. So this is exactly in agreement with this definition. So yes, in this definition, this is 1/2 spin, this is +2 spin, and so on. So this two-dimensional topological defects agrees well with definition of spin. But in 3D, it has to be a vortex, in fact. Yes, so this is not just, it has to be a vortex. For example, they call these quark strings flux tubes in QCD, this kind of vortices I will use. So we can also think about this G factor. It connects three types of properties. So, but the most important is the magnetic dipole moment and angular momentum. So these are dynamical properties of this picture, not structural. So the structural 1/2 does not get there. So we should have approximately 2 for leptons, because to multiply by 1/2 should be 1, because these both are dynamical properties. This 1/2 does not contribute there here. So here are spin-like topological defects, and for charge-like, we need to go to this hedgehog, to these point-like defects. So here is this 3D defect. Okay, so I had some, and for the clock, the field should constantly rotate. Yes, and we need some mechanism for this clock. I have mentioned. Okay, so let's look at this Gauss law and its topological version. Yeah, so we have this Gauss law and we have this topological version using curvature also. So in Manfred's Faber way, so we define this gamma as the connection, curvature as the cross product of two gammas, and we use standard electromagnetic Lagrangian with this curvature instead of the F tensor. Yeah, so we interpret F tensor as curvature. However, it is dual curvature, in fact, because if you use the original curvature, it will be magnetic monopoles. If you use dual, you get electric monopoles, as we know from experiments that we have only charges, not magnetic monopoles. Yes. So here you can see that the farther they are, the larger tension of the field. So it leads to this long-range interaction like Coulomb. So I will mention in a moment. So here is this Coulomb interaction. So literally we calculate Coulomb interaction as effective interaction between these particles. So we put two topological defects here of opposite charge in the bottom, of the same charge at the top, in various distances, and calculate energy by integrating Hamiltonian being sum of curvature squares. Yeah, so as for electromagnetics, interpreting curvature as F tensor. So here is this Hamiltonian. The question is how to choose this configuration. So here is approximation by Manfred Faber ansatz. So it should be improved. I mentioned in a moment. So we calculate this integral with cutoffs. Here there are cutoffs in the singularities. It has to be repair. And then from this integration, we get the points. And the line is fitting with 1/r Coulomb-like potential. You can see it is literally Coulomb-like potential. So we get effective Coulomb interaction for these topological defects. Yeah, so this is purely integration and of Hamiltonian being sum of squares of curvatures, and we get Coulomb interaction, effective interaction between them. So, but it has two approximations. So one is this ansatz instead of optimization. And the second is this cutoff around the singularities. So let's think about. So here again, here is the gamma, here is the curvature, and here are Manfred Faber serious calculations. So which optimize the configuration of the field, and instead of the cutoff, use the regularization, this optimization of the change of the length going out of the Higgs potential. Yeah. So doing so, he got slightly steeper Coulomb behavior. So the Coulomb force become slightly stronger in very short distances. So it means very high energy. So we see that Coulomb has to be slightly stronger for very high energies, and it is known as the running coupling, that the alpha grows for very high energies. So we observe it. The standard explanation is the vacuum polarization. So we have kind of alternative classical correspondence to this vacuum polarization here. So here are some arguments regarding size of the electron. So the one is the most known is based on G factor. So he has drawn in 1989 Delmet has drawn this plot. Here is G factor -2. Here is the size. He has drawn proton as made of 3 quarks, deuteron as made of 3 nucleons, and electrons as made of some 3 partons. So he probably tried to draw a line here, but doing so, he would get negative radius for electrons. So he extrapolated from 2 points using parabola. So it is complete nonsense. If student would do it, he would not pass the test. But Delmet was Nobel Prize winner, so everybody used this plot. So, but it makes no sense. A better argument is the scattering, electron-positron scattering. So here it is for very high energy in GeV, so 100 GeV. So what we can see in this log-log plot, that we have nearly linear behavior plus some resonances. So this is for extremely high energy. Why we are interested in the size of a resting electron. So we should extrapolate this line to the mass of resting energy, and we get approximately 2 femtometer size. And another argument that we should use is deformation, just kind of vacuum polarization is that disagreement with Cranach coupling. Yes, so I think it's the appropriate way to model the electron. Okay, so now let's go to the further particles, QCD. Yes, that's the most interesting, I think, part. Yes, so as mentioned, we need to add something to get the three leptons, not one. So we can start recognizing three directions, the field of three directions. So we get three hedgehogs, for example, which has the same topological charge. So asymptotically should behave the same, but have different mass, different regularization. So looking at this electron, it has to have these topological vortices. So it's unavoidable, but I think it's these color strings like in QCD. So now let's go to these quarks. Yeah. So having this Ablikosov vortex made of this field like here. So it prefers to be parallel like here. So here is the lowest energy state. But we can perform inward outward rotation. Yeah, so performing full rotation, we would get a hedgehog, we would get elementary charge. But we can only perform a partial rotation, like here and here. So here we make, let's say, pi third in one direction and pi third the other direction. So like for quarks. And in the middle there is some conflict, additional conflict, which should have some energy, asymptotically energy per distance. And it is known from QCD that it should be approximately 1 GeV per femtometer. So it sounds right. So here is a picture from QCD articles. So it sounds like reasonable in agreement with what QCD wants. And the question is why this rotation is made. I will show in the moment with the model of baryon. Yes. Okay, so let's look at the neutrinos and how I think neutrinos should be thought of. So neutrinos, so some people try to use just electromagnetism for neutrinos, but I think it's wrong. From one direction, there are massive, electromagnetism is massless. The other, electromagnetism cannot pass like 1 centimeter of lead, while neutrinos can pass to Earth. So they have some very stable, very strong mechanism to bind this energy of mass and to survive through passing to Earth, for example. Yeah. So they need topological mechanisms, I think, to explain that. And also they should be created by beta decay, and we agree with what I'm showing in the moment. So I believe I think it well agrees. If we take this color string, this Ablikosov vortex, and close it into a loop, and I think it agrees well with neutrino. So from one side there are t-types like here. So we can have a loop along one of the three axes. Yes. So we have three flavors here. Yes. They are very light and stable. Yes. And they should have these three masses, three oscillations. So we need this mechanism. Should be similar as for electron. So they use the same formula as for electron. So here I think would be this oscillation between a muon and tau neutrino. So literally this twisting of the field by 90 degrees. So it is the preferred oscillation between mu and tau, not electron. And this is also known from experiment that there is mostly between mu and tau. Electron is kind of behind. So we can see that this configuration for electron is very different from these two. Yes, so indeed there should be preferred electron muon and tau oscillation, and it agrees with the model. For electron clock, so this experiment I mentioned, it has slight difference from the experiment, like 0.28%. So I suspect that in fact electron has also this three types of clocks, but finally only one survives. So finally we have only So finally, they have to add to the project only to this 1 degree of freedom, which can oscillate there. Yes. So. Okay, so then there is this question why we have only left-handed neutrino and right-handed antineutrino, and again I think this mechanism I have mentioned should explain it, because I have shown this term which has both the gravitational part and this spatial derivative part, and assuming that neutrino and antineutrino have the same gravitational mass, this violet part. Antineutrino only changes this derivative. So indeed, the rotation should be in the opposite direction. Yeah, so it makes sense that they favor some chirality. So then there is energy conservation problem. So if being a loop, it can have varying energy mass. So depending on the length of the loop, it can have larger or smaller energy. So for example, during this oscillation, which changes the energy density per length, they can just vary the length. So we can the energy conservation could be satisfied here. In contrast, for leptons, we don't have oscillations because energy conservation that does not allow for that. Yes, because for here we can change the mass to change of length of the loop, but for leptons we cannot do it. Okay, so that also there is kind of Gaussian invariance inside. So looking at the cross section and rotating inside this cross section, the energy does not change. Both the regularization and the derivative is the same. So there is a freedom to rotate in the cross section. However, it's the same energy. However, from interaction perspective, it should change something. It's very subtle, but I think it could explain the sterile neutrino, that this rotation changed the strength of the interaction. So the sterile neutrino, instead of being separate particles, would be kind of different states of the same neutrino, which is more difficult to interact with. So I think it could explain the sterile neutrinos. Also, so here is antineutrino. The question is the cross section should be spin 1 or 1/2. I'm not certain. I think from the beta decay I suggest it should be 1. The question is what about the 1/2? So I have a feeling that 1/2 could be, for example, created in the Big Bang, but they are extremely difficult more difficult to observe than standard neutrinos. So they could be part of the dark matter, dark energy. This 1/2 neutrinos. So here are 1/2. Here is 1. Okay, so let's go further. Okay, so let's go to baryons. Yeah, so there was this question, why these quarks? So here are these 6 quarks now. So because we have 3 types of loops and 2 types of charges, -1/3 and plus 2/3. Yeah, so the question is why we have three colors. They call it colors because we live in 3D. So why you have 1/3 and 2/3? So let's try to understand it now. So 1/3, 2/3 is preferred. So here is suggestion from the structure of baryon. So I have many arguments that the simplest knot, that is, we have this vortex and another around, seems to agree with baryon. So why? Because here we look at the cross section. The loop around interact with the loop inside. It deforms the field inside, and it deforms into hedgehog. So this interaction prefers some charge, which doesn't have to be full charge, it can be fractional. So for example, for proton, it can just enclose this hedgehog. For neutron, it has to compensate it. So let's say this enforce is 2/3, like for up quark, and so if it's enforce plus 2/3, then it has to be compensated to 0. So we have 2 minus 1/3 to compensate it to 0. And this compensation increases the size, what is costly energetically, so it increases the mass. So this way we get explanation why proton is lighter than neutron. Yes, because proton just encloses this hedgehog and neutron has to compensate it. And from the quark perspective, we know that U quark has lower energy because it is preferred by this loop around. Yeah, so we get this explanation why this U is below and the others are up. Because 2/3 should be more costly than 1/3, but U is below. And why? Because of this loop around, which enforces this some charge inside. Yes. So here are some experimental charge distributions of neutrons and protons. So for neutron, it is known that there is positive core, negative shell, exactly as here, positive core, negative shell. For proton, it's only positive energy. So we have these quarks, but they should be kind of nearly glued merged into one to get this charge distribution as in experiments. And we have these two mixing matrices, the CKM and PNMS, for CKM for quarks and PNMS for neutrinos. So you can see that this PNMS is much more free. We can freely rotate between all of them, while for CKM, it's much more difficult. So why it's much more difficult? Because of the loop, which stabilizes the field. Yes, so we can intuitively at least understand why the CKM is much more difficult to mix than for neutrinos. All from just geometrical interpretation of the standard model with massive neutrinos. Okay, okay. So here are some articles with charge distribution of neutron as mentioned. So we had all claim positive core, negative shell as predicted by this model. So also this negative shell also can be seen in this negative G factor of neutrino. Then we can go to deuteron, the simplest nucleus. Okay. So we look into going to deuteron. So here both require this charge, like here, but so here they can share with one charge between two baryons. Yeah. So here the energy is reduced thanks to sharing of one charge. So what we get, we can see that we get plus minus plus. So we get electric quadrupole moment. Automatically, this model suggests it should be quadrupole moment. But if you think about proton plus neutron, it shouldn't have electric quadrupole moment. But the experiment says that it has. Yeah. So it is an agreement, and I view it's not. So indeed it should have electric quadrupole moment, and it has here. Then another argument is that the magnetic dipole moment of deuteron is nearly the sum of the proton and neutron. So there should be aligned spins, angular momentums, and it is also in agreement here. Yeah, so extremely simple model. Just looking at liquid crystals, we get the entire standard model. Yes. So these are the conclusions from this looking at this liquid crystals picture. Okay, so then the question I think is that so we have this. They believe there is this string between this color string flux tube between quark and antiquark with increased energy inside. And the question is, does this string end at the quarks or maybe go farther? So if it's because of vortex and also the model, it has to go farther. So are there some arguments that it goes farther? I think there are. So for example, there are halonuclei, like lithium-11 having single neutrons, like 2 neutrons in distance like 5 femtometers. So 5 femtometers is much larger than of standard nuclear force. So the question is, what binds them for like milliseconds here? It's so large distance. So in some binding mechanism, and saying that there is this kind of vortex topological binding them, I think it's I don't know. It's a good explanation. So it's a nice argument that maybe there is literally some vortex going to bind them, and there are also these. They also call them these Borromean halonuclei, that there are these rings that if you break one, all will fall apart. And experimentally they say they get 3 nucleus forces, like here. So here is distance between the two neutrons, distance between center and the neutron, and they get waves which has to be asymmetric. So they require 3 body forces here. So the question is how to get 3 body forces. And again, saying that there is some literal one-dimensional vortex could give the 3 body forces. Yeah, so finally we can try to see the nuclei as these knots bind with these because of vortices. Yes, here against the Coulomb repulsion. So there are some also more arguments that there are these one-dimensional because of vortex topological structure in vacuum, especially the sun's corona. They see the bright lines in the sun's corona, and they don't understand why they are so stable. And again, maybe they have topological nature, like being this color string flux tube because of vortex. Okay, so finally we can think about the hadronization they see in colliders. So they smash these two protons, lead atoms, gold atoms, and then get a lot of particles. And the basic model is the string model. They assume that there is maybe this one string, this color string, flux, gluon flux tube, and it decoys, reconnects and decoys into mainly pions, baryons, but also neutrinos, finally leptons from the Chi. So the question is how to get it. And so again, we can think about this very long high energy string, and it reconnects. And the question, into what topologically we can reconnect. So we can form a simpler loop, like for neutrino in this interpretation, machine interpretation. This loop can be twisted, like in a Möbius string, Möbius stripe. Yes. So there are many arguments that it agrees with the strangeness. And finally, it can form knots. And as mentioned, the knots seem to agree with baryons. So there might be also much more complex situations, more complex configurations like this interleaving torus like options. So there is a space, topological space to get some more complicated particles, metastable states. So it needs to be explored to get the full agreement with these thousands of particles they observe in experiments. Yes. So, but there is the freedom in topology here. So maybe let's be briefly think about this strangeness as this internal twist, like this Möbius strip. Yes. So if this count, or if it is not with some central, it would be strange baryons. So it kind of releases the strangeness and produces pions. So these simple mechanisms seem to agree with basic modes they observe. This omega drops by one strangeness to Xi, or by two strangeness with count to lambda. This Xi drops with one pion to lambda, and lambda drops to proton or neutron with one pion. So it seems to agree with this kind of mechanism. Okay, so maybe let's take a look about some problems with the current view on the standard model of the QCD. So some issues. So what are issues? So one spin crisis, that the quarks that don't seem to give all the energy. So here we also need this energy of these gluons, which is this derivative along this tube because of this change of the potential. So we also need some gluons. Angular momentum, I would suspect that this loop around maybe also has some own angular momentum additional. So I think it's in agreement. Then there is proton radius puzzle that scattering with electron and scattering muon gives slightly different radii. So here I would say that muon and electron are asymptotically the same, but have field rotated by 90 degrees. So in scattering, they have slightly different behavior. So I would say that it is the matter of using electrons as muons. With towns, probably they would get also different value. Then there is this issue of neutron lifetime puzzle that for resting a neutron they have one time, and for active beam they have a longer time. So I would so there is no nice tuition. I agree with that might be because of some internal excitation of this neutron. So this is active neutron. So this is a complicated structure which may have some excitation which has to cool down before starting to decay. Then there is EMC effect that the quark distribution in nuclei should be different, looks different than in single nucleons. So as mentioned also with this deuteron model, yes, there should be some shift of the quarks inside when forming a nucleus. So I think it's also basically in agreement with the model I'm talking about. Then T-neutron forces, I think, through these vortices. Deuteron quadrupole moment, yes, because both the baryons require charge in this model. Halo nuclei, again, I think with the vortices required. Okay, so let's go further. So the scalar symmetry Becky I mentioned, I think it could be in solution, not in Lagrangian, but maybe there is needed some additional term to Lagrangian. I'm open, but I think it is sufficient that they have the same gravitational mass, but opposite spatial derivatives, or what should rotate, what should reverse like this left right-handedness for neutrinos. So here is the summary, but maybe let me skip it and finally try to go to the end. Okay, some applications. So the question is if the proton decay can be if there is possible proton decay. So in this model, as QMFNoT, yes, in theory there could be possible proton decay. So it is required both in baryogenesis that there was more matter than antimatter from the Big Bang, the Hawking radiation, that we can take baryons, squeeze them into black hole, and wait when it evaporates and get the MC² energy, fully transforming them into from matter to an energy. So the question is, could we gather this energy without black hole directly? So maybe having this kind of models, maybe we could try to think how to swing it out from this minimum, how to destroy this QMFNoT, for example, with some concrete frequency, maybe incoming proton beam with some incoming photon beam, and also some collision, to optimize the parameters to get increased probability of proton decay. But I think we shouldn't search for it in these huge tanks of liquid. Instead, should search for it in colliders or this kind of high energy situations. Okay, so some mathematics. So they are these two types of model: Austin-Frank basic model, similar to Faber approach, and which is generalized to the final model they use, the Landau-de Gennes. I'm also using. When we recognize the three axes. So here is the Lagrangian. Here is the slide I have shown. This is the Lagrangian. Maybe let me skip it. Here is going to gravity. Yes, so indeed we have this interaction. We have this second set of Maxwell equation. We have interaction between them to get, for example, the light bending, the gravitational time dilation. Then there are some discussion about the coefficients, but let me skip it. Okay, so let me skip it. So it degenerates to Manfred Faber's approach if forgetting about this twist. Indeed. So some search for Euler-Lagrange, for Hamiltonian. Okay, so here is some mathematical search for the Euler-Lagrange equations, and indeed getting Klein-Gordon-like equation for these twists, and Maxwell-like equation for the fields. Yeah, so we get electromagnetism for spatial rotations, and for okay, so here is. Oh, I don't remember. Okay, so okay, some Dirac equation, but I wasn't able to get. But so looking at this Klein-Gordon-like equation, also we can get the second set of Maxwell equation for gravity, looking at interaction of boosts. So here it is. We forget about electromagnetism and just look at the boost, and indeed we get Maxwell-like equation from Euler-Lagrange. And so there is the question of Newton attraction and repulsion. I don't have fully answered. I think that the clock is crucial here. And so here is this clock discussion. So having the standard FNF Lagrangian, it gets to Hamiltonian having only positive contributions, but using 4-index Lagrangian as we need for full curvature. We need to get also these negative terms, which seems to agree with the clock, because it favors, as mentioned a few times, it favors, so this term is energetically preferred. So twisting the field in gravitational field is energetically preferred. It has also penalties, but finally, hopefully, we should get the clock as observed in the physics for electrons, for neutrinos, for BB-bar oscillation, and so on. And here is the final slide. So here is the standard model. So it is kind of it works great, but it's kind of epicycles. Yes. So it didn't work. So they guessed and fitted new terms. So the question is, could it be simplified? For example, maybe it is some Taylor series of some simpler models. So, but the question is where to search for such a simpler model. So I think this simpler model I have mentioned, just liquid crystal-like we've just replaced the kinetic term with electromagnetic like, seems to get very nice agreement, unifies electromagnetic quantum mechanics and gravity, gives the leptons, neutrinos, baryons with proton, lighter neutron, deuteron, and many others. So it looks like that it's very nice way to get a deeper theory, which should be effectively described by this huge Lagrangian. I hope, but it's difficult mathematics, so I'm glad you collaborate. So thank you very much. Let me now stop the recording.